Hello, my name is Howard Penrose, and I'm going to guide us through a series of presentations that are planned around the concepts related to tying energy and emissions to reliability and maintenance. Well, as we often state, you cannot manage what you cannot measure, and there's a lot of things that we keep trying to tie to reliability and maintenance programs that do not tie and do not measure back to programs that the C-suite basically pays attention to, as well as other management within the company, corporate goals, and everything else. 2003, when a motor diagnostic and motor health study was originally performed, we found that about 3% viewed energy as part of the reliability metrics. 2013, this value dropped to 0. It's pretty much remained constant until recently, when everybody dove onto the emissions train. Now, for those of us who've been doing it since the early 1990s, it makes a lot of sense. And part of the reason is because, well, as we say with other things, a more reliable system would be more efficient. If I'm looking at precision maintenance, I'm looking at improving my efficiency, and therefore a direct tie from any energy loss back to emissions, etc. So when we started looking at this from certain standpoints, and that's what today's presentation is about. Today will be the longest. The remainder will be series of 5 and 10 minute programs. But we saw reliability as part of energy improvement, not the other way around. And energy, then again, as part of that reliability improvement. Then we looked at applying just a predictive maintenance program alone. Now, this was determined through Rutgers University's program with the U.S. Department of Energy being at least 14% improvement in energy cost just by going from a reactive program to a planned maintenance program. What we've generally seen is this number can go up by many orders of magnitude, whether I'm looking at reliability improvements such as reduction in harmonic content and power, air leaks, or even problems such as going to energy efficient programs and forgetting to do things like filtering, power harmonics, and so on. Energy related improvements can be quickly documented through simple measurements, and even more importantly, those measurements will tie back to an actual change in cost. And that change in cost is going to depend on the type of application. So if I'm looking at a commercial building that's operating at a constant load, I will see that measurement drop significantly. If I'm looking at cost per unit of production in, say, a job shop or a variable production facility, we need to manage whatever the baseline is and then what the variable costs are associated with energy of all types. There's many ways to do this. And then we need to be able to then tie that back to emissions, which is not that challenging. As a matter of fact, it's relatively simple. Energy is in the P&L for a company. Emissions are probably part of the corporate goals, especially presently. Cost avoidance is not. I often have referred to that in the past as magic numbers. The bearing might fail in the future per a predictive maintenance program or failure finding program, basically, and therefore we avoided this cost. Well, that doesn't relate to anything. It really doesn't. I mean, how I would look at my P&L and say, well, I don't have a column for that. And then another thing to remember is correlation is not causation, which is a scientific statement. That means that, well, we know that things such as safety are affected by our maintenance and reliability program. We're just using it as a correlation. It does not mean that it's a cause. So let's take a quick case in point. There is a known method for measuring energy losses in, say, a compressed air system, and that's what is the pressure drop. So going back to the Department of Energy's methodologies, let's take a look at an entire system. I mean, normally when I go in and I take a look at a system in order to determine whether or not I have an issue, I start at the top. So if I'm going and looking at an electrical issue, I start at the utility meter and then work my way through the plant. So if I'm going to go to a compressed air system, I'm going to take measurements off of the actual system operation and then what the overall pressures are. So if I have a 100 psi system and at the end of that compressed air line I only have 45 psi, that difference at 55 psi are air leaks. So if I have numerous air leaks and not all of them are audible, I would take a power measured. So in this case, unless you're looking at steam turbines, that we'll cover in another presentation, but let's just say it's all electrical. So let's say 0.5% times the pressure dropped times the power measured gives me the actual losses associated with that pressure drop. So if I take a look at this particular application and I have 220 kilowatts, and by the way, in this particular application, part of the problem we were running into and part of what we were investigating is that the air compressors were heavily overloaded. That 60.5 kilowatt drop means that is 60.5 kilowatts we don't need to be using. So by addressing the leaks in the system, we can look at the total costs being in demand at $14 per kilowatt and 7 cents per kilowatt hour. Those numbers have changed dramatically recently, but that's neither here nor there for this presentation. But 60.5 kilowatts times $14 per kilowatt across 12 months, that's about 10 grand. And then if we take charges, which is our usage, that's 60.5, say we're operating 8,000 hours, at 7 cents per kilowatt hour, that's 33,000. So we're talking about $43,000, about $33,500 approximately, is what we're losing due to just air leaks. Well, let's take a look at the tie. Now, we're going to talk about in the very next presentation we do next week, we're going to talk about where you can get these numbers and how to apply them. So let's say 60.5 kilowatts times 8,000 hours. We'll convert that to megawatt hours by dividing by 1,000. That's 484 megawatt hours. In 1999, in Illinois, where this was tested, we were at 0.75 tons per megawatt hour emissions. That comes out to 363 tons CO2 per year. That means that in addition to reducing my cost of operation, I also start addressing the reduction in CO2 emissions. In fact, part of what we discovered in the 1990s in all of the challenge programs associated with the Department of Energy was that maintenance and reliability were the #1 methods for reducing energy in a plant, even over the application of energy efficient technologies. So let's take a look at this particular one. Compressed air systems, it takes 9 horsepower to make 1 horsepower. In another area of the same plant, we had 1/2 inch opening, 150 psi. There's a calculation for coming up with this, which is the amount of air lost through that opening. In this case, it was 120 kilowatts coming through there. As a matter of fact, in their on-site generation plant, we were able to close this valve and measure the reduction in consumption. So 120 kilowatts times $14 per kilowatt times 12, that's 20,000, 120 kilowatts, etc., 67,000, so $87,000 right there. Well, I didn't put down the amount, so let's say 120 times 8,000, a second to start up. So anyways, the blow-off valve cost at the time was about $1,000. So let's say 120 kilowatts times 8,000, we're just going to call it 8 for that. That's 960 megawatt hours times 0.75 for that area. That's 720 metric tons of CO2 that will reduce. We won't avoid, will reduce. So that is a measurable value before and after. Supply improvements. So in addition to power factor stuff and so on, actually power factor doesn't reduce energy costs. It improves the capacity that you'll have in a facility. It'll do some other improvements. It will reduce some very small I-squared-R losses overall. It does have a downside though. Apparently, when we have high harmonics in the system, my power factor correction capacitors become a load, increasing my costs even more. That's something we're going to cover in the future as well. Let's take a look at a ridiculous loose connection, because we would probably be burning the plant down. But loose connections make up about 1/3 of supply problems. Matter of fact, loose connections in a system make up about 0.2% of the energy cost improvements, or can reduce your cost by about 0.2%. So an example of, say I have 100 amps at a 1/2 ohm. Now I-squared-R works whether I'm talking about AC or DC. That would be 100 squared amps times 0.5 ohms. That's 5,000 watts or 5 kilowatts. And if I start calculating that out, I come up with $3,600 a year and 30 tons of CO2. Now, is that too ridiculous? Well, we've seen a few something like this. As a matter of fact, we've seen loose connections or even other things that have generated single-phase conditions in a machine that will run along the same type of lines, because the drop goes across where it is. In this case, I've got a slow blow motor fuse, I've got a fast blow fuse, and then I've got a lighting fuse here. The lighting fuse, when we were testing, because we got a really odd reading when we were doing our energy analysis, that was single phasing that 100 horsepower motor. Controls such as variable frequency drives, changing from DC, using it in the application of pumps and fans and everything else, it changes our reliability issues. A lot of times it'll move some of the problems we're having from elsewhere in the system back to just the motor and pump, or motor and fan, or motor and compressor. However, what we seem to forget is harmonic content adds up in a system. So where we're supposed to do things like IEEE 519 and the point of common connection with the utility to protect the utility, we end up with a whole list of other issues such as harmonics, ground harmonics and voltages and currents, and neutral currents, depending on the type of nonlinear loads we're adding to the system. In some cases, we've even found where people have gone to LED lighting after having originally gone from, say, T12 type bulbs at 40 watts per bulb, and then they'll put in a T8 or T5 and drop down to about 32 watts per bulb. Then they put in your newer lamps, and they put those in, and supposedly we're now down to 6 watts, I'm sorry, only to find that the harmonic content associated with LED lighting brings us back to over 40 kilowatts because of all of the losses in the system, and nobody thought to filter anything. So we're definitely going to be talking about that as we move forward in these series of presentations. Very simple ways to make improvements, things to consider when you're speccing things out, all that will have a direct impact. Repair versus replace decisions. So going from older efficient motors to higher energy efficient or premium efficient motors, You can measure the kilowatts before and after, such as this case. We're going to talk about this a fair amount in the future as well. You're not just talking about a reduction in energy, but as a direct result, a measurable value in emissions reductions. And we're also definitely going to be talking about things such as the software tools that are available through the Department of Energy at no cost to help us calculate all of this. And the other online tools available through EPA, EIA, and DOE. So let's talk real quick about the origin behind what I was doing. So I'd been doing it for a while. I was working on my dissertation. I was also teaching at the University of Illinois, as well as being senior research engineer at the Energy Resources Center at the University of Illinois. We did a project with the Illinois Department of Commerce and Community Affairs on food processing. My students, my industrial engineering students, needed a project. And instead of doing the usual, because we were attached to the mechanical engineering department at UIC, we said, okay, instead of designing a bumper or something like that, let's give them a fighting chance to win some awards. So we got the students involved in one of the projects, and it had to do with the process improvement, the Illinois food and kindred products. And I said, why don't we take a look at how we do industrial assessments to maximize the results? So here's some of the actors involved. I was both the senior research engineer for UIC ARC, but I was also the industrial engineering student advisor in relation to this project. Wai Chin Kyle Kim ended up going to Northern Illinois University, and some of the others were also industrial engineering. Robert Miller happened to have been former chief on board my aircraft carrier when I was in the Navy, and this was kind of neat having it back. All of these other folks have gone on to senior positions with their companies in industrial engineering and logistics. So the project concept was to develop a model for industrial assessments and then develop an interactive opportunity or interactive opportunities in energy, waste stream process, and reliability. And of course, emissions all went along with that. And then, of course, developing field case studies. For those who know me, yep, that's me back when I was much younger. And then those were the others involved in the project, that particular one. Part of it also involved going out and finding software tool selection. So in the near future, I'm going to be talking a lot about machine learning, AI, and all that other stuff. It's not new. We've been doing, well, the concepts behind machine learning and AI and all this other stuff started out in the 1950s. So everybody thinks for some reason this is all new stuff, and it's not. Stuff is miniaturized. The direction of the World Wide Web, communications, and other tools have allowed us to expand upon what we were already doing. And the problem is the accuracy hasn't really changed so far. So that is part of the issue. There's a lot of biases involved and so on. So whenever I talk about modeling, we're talking about using the tools that are available to us to go in and simulate what we want to do. Now we can also take in all the information. There were ways of doing it before, but prior to 2007, most of our portable computers or desktop or laptops all had single core. If you were, that was about it. Single core systems. Wasn't until 2007 that we had multi-core systems that had the processing power that allowed us to do real machine learning locally. And now with advances in technology and software such as Python and R and all of the other tools and languages that we use in order to do what a new term for what we do as industrial engineers called data science, which came about in 2015. I guess there's a war between University of Michigan and MIT who came up with that name first, but basically data science allows us to take a look at all of that data, look at it closely and say, what are the patterns we're seeing in it? Going back to what we were doing with the larger systems back in what I was doing with the larger systems back in 1990s, even in the 1980s, when I had access to the Argonne National Lab system. So when we did the study and we took a look at all of these opportunities, we found that in the site opportunities when doing a proper survey would have about 30% process improvements, 10% waste, 10% energy, with usually zero cost applications, just simply doing what you're supposed to do in the first place. I remember one time we went in to this 5,000 square foot bakery and they wanted to reduce their cost per cookie by 0.1 cent or something like that. We gave them 2 cents per cookie, and the main thing was that their cookie cutting machine, they when it had broken down, it was a European machine and it had metric components in it. They went out and they got bolts and everything else that were English, didn't tap, just drove them in there, and so eventually things would break almost on a daily basis, and it became routine. And was that limited to there? No, we've been into major corporations. As a matter of fact, to this day, when I go into major corporations, I'll ask a question like, well, how often are you changing VFDs? Especially if I see like high harmonic conditions or poor grounding conditions. And they'll come back and they say, oh yeah, we replace 2 or 3 a week. Well, how long is a VFD supposed to last? 15 to 20 years? So when you're replacing VFDs like candy, you've got a problem and you have to investigate it. Once you start identifying that, because the driving force behind all of these failures is lost energy, that lost energy goes somewhere. By correcting the problems, reducing the lost energy, you improve the long-term reliability of your systems. Initial site evaluation for that plant, we found a 40% improvement in production, a 66% reduction in waste, 3% effectiveness, all with 6% energy improvement, and that included changes to production, which improved the throughput, changes to product flow, improvements in that one device. We went out, drilled and tapped and put in proper bolt sizes, and then workflow and other reliability issues, including things like gaskets on the freezers. So, yeah, as a matter of fact, here we go. New floor plan. When we did the simulation, we found that employees were like running into each other. Well, then we went back and we observed that, because you never trust software for everything. You always use it to identify the potential problems and then go and verify, right? Inventory systems, having give the supervisors better tools, and then applying a simple PM, PDM, and corrective maintenance program. Ergonomics, making it easier and safer for the employees, actually increased productivity. Most of the time, ergonomics is not something that goes against the operation of the company, but properly applied ergonomics improve throughput. Energy and waste stream measures, and of course all of that tied back in, to a reduction in emissions per unit of cookie. The lessons learned, basically the opportunities that we had in true industrial assessments were very dramatic. I've applied them the rest of my career. I mean, I do a lot of troubleshooting, but usually when I'm going in, I'm looking at it from the eye of an assessment, looking at the entire system. What are the effects of doing this particular function or that particular function, and how does it impact the entire system? Occasionally, improvements in one area will have a negative effect. Like I said, we start putting in all of these new nonlinear systems, lighting, VFDs, and everything else, can have a negative impact on your energy emissions, reliability of different components, and so on. All of it has a huge impact on waste product, process, energy, emissions. And then the recommendations in all of these cases we found paybacks in less than 1 year and sometimes instantaneous. And through all of it, and what I had to teach my students in particular was don't sweat the small stuff. Look at the bigger picture, see how everything's operating. Don't worry about the decimal points until you've identified where the issues lie. Usually the observed conditions are your fuses, right? The points, the weakest point in the system, but does not mean that that's the problem that you're trying to solve. So let's take a quick look at this. 50-acre facility. We set it up in 2 phases. The first phase was lighting survey and observations, a walk through the plant. This was all done, by the way, we were given 5 days on site. This company doesn't exist anymore. This was 1998. Phase 2 was going in and doing a motor master survey, looking at motors in an area, doing compressed air, steam leak, gas dryer efficiency, and pump seals. Yes, even pump seals are an issue. Now, mind you, we had a lot of fun. They made bourbon there. It was a corn miller, so there's a specific process to what they did, plus a lot of compressed air. And then we found, when we did our assessment, that 91% of all the electrical energy at that site went through electric motors. So we did a broad motor analysis. We developed repair versus replacement a program with them, identified new VFD applications, identified problems with the existing ones, and recommended some upgrades, and then also discussed the maintenance and management program there. They did have on site an 18 megawatt cogen plant, which dropped their cost significantly. As a matter of fact, they were an exporter of electrical energy, so they had the utility running their cogen plant. We found that they do, without the thermal credit, they were seeing, with cogen systems, you have your direct emissions in CO2, which in this case was about 8 tons CO2 per 1,000 pounds of steam. Then you have your corrected or thermal credit amount, because you're taking what you're generating and you're using it as another form of energy. So however that came up, but that comes out to roughly 1 ton of CO2 per 1,000 pounds. So we took a look, just in a walk through the plant, we found steam traps. Now, on average, if you don't have a steam trap plant practice in place, expect about 10% of your steam traps will fail a year. That is a rule of thumb that we applied in the 1990s and still exists today. So the steam traps that we identified came up to about $7,500, or about 1,800 tons of, or almost 1,900 tons of CO2 per year. Leaks, just leaks like this one here on the left, and then this one here, which is a hose, steam hose that was just left sitting there. When you get this many acres, you're going to have stuff like this. That came out to 33,000 or 8,400 tons of CO2 per year. And then excess energy, whenever you see steam blowing out a pipe constantly in the plant, that just means it fell under the pressure. So in this case, the lowest pressure they used was 40 psi. What was coming out of here was roughly 20 psi, and hence the plume. That's not contamination, that's literally moisture. That excess being blown out is potentially worth $186,000, or almost 47,000 tons of CO2 per year, which is ridiculous. That's 47 megatons of CO2 per year blown out stacks. Why not take that, recompress it, and reuse it? Lighting retrofit, when we went through, we saw potential for 300 kilowatts. That's, basically came out to about an $80,000 investment and a 1.7 year simple payback. Savings about $48,000. That was just going T12 to T8. The numbers with some of the newer systems are much higher, as long as you apply some type of filtering system to avoid your losses in harmonics. So the weighted average there was so much, and then that avoidance came out to be about 900 tons of CO2 with that existing mix of energy in that area in the late 1990s. That value is much lower now. It's almost, well, drops by about a third. I think it's about 0.498 now because of the nuclear power plants and renewables that are in the area. Now, other waste stream stuff were things like, well, this picture here, we had a leak that came out to be about 5 gallons per hour, and they tried to bind it with cloth taped and tied around the pipe, but we put a 5-gallon bucket up here and just collected 5 gallons per hour. There it is again. And then also wastewater leaks. They had product leaks. This had to do with a seal issue. We'll talk about that in a little bit. That was all over the place. There was not a non-leaking seal in the plant. Now, the problem is this all goes into their waste treatment plant, and that generates a lot of energy loss there because they have to return water cleaner than they take it in from the nearby river. So the maintenance and reliability aspect, they had a very not well-run vibration program. We recommended that being brought up to speed. An infrared program because they had loose connections all over the place, and nobody would. Well, and then of course, just like some other facilities I've gone into, the recommendation of shutting things down and then doing IR is kind of ridiculous, but people do that. Motor circuit analysis to test the condition of electric motors, and then finally electrical signature analysis to look at system improvements. The pump seal issue, because we saw pump leaks everywhere, and all of this stuff ends up getting washed down and going through waste treatment, and that's MASH, that's actual product. Presently, at the time, I should say, they were paying about $114,000 per year in pump seals. Somebody had come along and thought that they would save money by going from a double seal that these were all originally designed for and switching over to a single seal, which were only lasting about 3 weeks before they'd start leaking again. And then they'd have to go through there, which that didn't just waste time of everything. That's a wasted time of the maintenance staff who were then no longer doing their planned maintenance. But we saw that as a simple 3-month payback by going back to the original seal types that weren't leaking very often. Process heat was huge. If we get it, well, we will eventually go through things like process heat and heating systems overall and the energy associated with that. But let's get back to some concepts here. Implementing a project of this type, getting a team together, just like doing an RCM or something similar, selecting simulation software, developing your own, or using an existing one. Personally, I like developing my own because then any biases in there are the biases that I or my team have introduced instead of what somebody else has introduced for whatever their purposes are. Model existing systems, including support systems, perform an energy and waste stream analysis, model recommendations, develop an implementation plan. If you don't plan it, it's not going to work. I've watched people go in, and also, by the way, start with a small area and then expand it. I've seen far too many times people will go in and they will try to do everything all at once. So back in the day when I was at General Motors and we went to apply programs, we would start in small areas and then expand outwards. And those programs existed and continued to exist. And we also did that at a steel plant where all of a sudden people were going, hey, we want to be part of this too. Once you have the requests, then there's buy-in, then you're going to do well with your program. In any case, we also went ahead and created additional studies to prove our point. one at a paperboard plant, one at a frozen food company, coal-fired power plant, which has been decommissioned, a confectionery facility, candy is good, commercial buildings, the Brookfield Zoo, Museum of Science and Industry, and then some of the steel and casting plants. And then issued that, in the end, as a novel approach to industrial assessments for improved energy, waste stream process, and reliability, which became my dissertation. And with that, I'd like to thank you very much. We will continue this series in 5 to 10 minute increments down the road to teach or show, demonstrate how to do this and where the resources are. The next one we cover, we're going to stay in the electrical area, and we are going to talk about how to figure out how to calculate your emissions, and then we'll go from that, which that's going to be nice because everything else is going to build on that. Then we're going to start into electrical management and how to get actual measurements and how not to get fooled. In any case, that's it, and thank you very much for your time.